Greetings, welcome and welcome again to this course. Last two classes we have talked about turbulent flows characteristics, then we learned how to derive governing equations for turbulent flows. In today's class we will continue that exercise, we will try to understand more about Reynolds stresses, how to model the Reynolds stresses and different approaches available to model these Reynolds stresses. Then we will see whether we can do something about introducing standard turbulence model. I rewrite here the governing equation for turbulent flow, which is specially called Reynolds average Navier-Stokes equation RANS. We understand terms in the equation, two terms on the left hand side, time derivative term, convection term, the right hand side pressure gradient term, then the additional term which is appearing because of the time averaging procedure is rho u I prime u j prime bar, and this term appears from the convection term. For the sake of convenience, we move it from the left hand side to the right hand side, and it is grouped along with the viscous stress term. You can also check the unit wise rho u I prime u j prime, it has the same unit as a stress term. In the expanded form, that is by substituting values for index I and j and following that guideline for index notation, we are able to write detailed of each terms as shown here, and these terms are additional in the Navier-Stokes equation and they are referred as Reynolds stress term. We use a symbol either tau or Rij equal to minus rho u I prime u j prime bar. Now, we put only the stress term in the form of a matrix as shown here. So, we learned that along the diagonal you have the normal stress term which is represented as a sigma, and off diagonal elements you have a shear stress term which is represented as tau. Now, if you look at the shear stress term, for example, the first row you have rho u prime v prime bar and rho u prime w prime bar, and you look at the first column second row. So, rho u prime v prime bar, first column third row u prime w prime bar. So, if you look at first row second column, that is rho u prime v prime, first column second row element rho u prime v prime, they are same. Similarly, the other component u prime w prime, that is the last element in the first row, and first column last element u prime w prime, they are same. Hence, originally we have 9 unknowns, 3 by 3 9 unknowns, 3 diagonal elements stress term and 6 off diagonal element shear stress term. Among the 6 off diagonal element shear stress term, only 3 appears, they are symmetric, right, they are symmetric with respect to diagonal. So, those 3 terms which appear on one side are same as 3 terms that appear on the other side. Hence, the total number of unknowns, though it appears 9, it is actually only 6, that is 3 along the diagonal and 3 off diagonal. Total we have 6 unknown, 6 additional stress or 6 Reynolds stresses, unknown stresses. In the standard notation form, the same equation can be written using a time derivative plus local plus convection term put together as a total derivative on the left hand side. Then you have pressure gradient term on the right hand side. Then we have laminar stress term and turbulent stress term. As I mentioned in the last class, laminar stress term and turbulent stress term, they are brought in the same way. You compare the order on the role played by each term appropriately to apply it for turbulent flows. Now, the job is to model these unknown terms. There are 6 additional stress terms, and the procedure to model these 6 additional stress terms is what is known as a turbulence modeling. We learnt about closure problem. What is the meaning of closure problem? We revisit that again. Originally, we have continuity equation and 3 equations as a Navier-Stokes equation. So, there are 4 equations and there are 4 variables, 3 velocity component and 1 pressure term. So, number of equations equal to number of variables is satisfied. In turbulent flow, we have additionally 6 stress term, whereas number of equations remains as 4. Hence, we have total 10 variables, but number of equations as 4. Hence, it becomes a closure problem. There are 2 ways of solving this closure problem. Either in some way or other you get additional transport equation or PDE, or suitably replace the unknown variable in terms of known variable. That is what is known as a turbulence modeling. In turbulent flow, if you try to derive additional equation, it is possible for each fluctuating quantity separately, also for stresses, and if you happen to do, then you will notice at the end it only results in additional unknowns. Hence, the closure problem remains. In the next few slides, I am going to explain how this actually will happen. So, the alternative is to replace suitably unknown variables in terms of known variable, and this procedure is what is known as a turbulence modeling. We use a concept called eddy viscosity concept proposed by Boussinesq, and this eddy viscosity is something like how viscosity is playing a role in laminar flow. The turbulence is characterized by an isotropic eddy viscosity. In more generic form, it is called eddy diffusivity, which helps in enhancing mixing between various constituents of the flow. And based on dimensional argument, eddy viscosity is proportional to density multiplying by eddy length scale and multiplying by eddy velocity scale. So, in a flow you will have all the 3 scales, length, velocity and time scales, and we know they are all related to each other based on dimensions. So, if any 2 quantities are known, it is possible to find the third one. We use same symbol mu with a subscript T to represent eddy viscosity. So, eddy viscosity mu T is defined for a turbulent flow, and it plays same role as the fluid viscosity. We already know mu and nu defined for laminar flow. The kinematic viscosity or dynamic viscosity is fluid dependent. That means, you may have air, you may have water as a fluid media. Kinematic or dynamic viscosity is fluid dependent, whereas the eddy viscosity is a flow dependent. That means, for the same fluid, for example, water you are dealing, depending on the flow condition, it may be varying spatially as well as temporally, whereas the dynamic viscosity or kinematic viscosity is fixed for that same fluid for the same flow problem. The starting point for all the turbulence modeling is a Boussinesq eddy viscosity assumption. It is used to predict properties without having to know any prior knowledge about turbulent structure. Now, let us define some more quantity, what is known as a turbulent length scale. We use letter L and it has a unit as m meter. Turbulent kinetic energy symbol K which is square of the velocity. So, meter squared per second squared, turbulent dissipation rate epsilon, which is rate of dissipation of energy. So, it becomes meter squared per second cube, sorry. Then specific dissipation rate omega, which is 1 upon s. We also define turbulent eddy viscosity mu t, and it has the same unit as the laminar viscosity kg per meter second. Turbulent kinetic energy, dissipation rate and specific dissipation rate, they are all related to eddy viscosity based on dimensional arguments as shown here. So, mu t is equal to rho k over omega, or mu t equal to rho k squared over epsilon. It is also possible to relate these three quantities based on again dimensional argument. For example, L is equal to k to the power of half by omega and epsilon equal to omega into k. It is possible to write separate PDE, other words transport equation for each one of these quantity, turbulent kinetic energy, dissipation rate, specific dissipation rate or length scale, and you solve them, you get respective variables of time. Then the turbulent viscosity is calculated based on the relation that we have just now shown. This is then used to replace the unknown Reynolds stress based on Boussinesq assumption. So, unknown Reynolds stress term is ui prime uj prime bar, either we can use r ij or tau ij, is related to mu t if you use rho on one side, otherwise it is nu t because mu by rho is nu and t stands for turbulent flow. Then you have velocity gradient term minus 2 by 3 k delta ij. We already learned delta ij is Kronecker delta, and that takes a value of 1 if I is equal to j, equal to 0 if I not equal to j. So, this was a proposal by Boussinesq, and this is a starting point, foundation point for all the turbulence modeling. Depending on how these relationships are set up, you get different turbulence model. The turbulence model have been in existence since identification of laminar flow and turbulent flow in a flow regime. There has been a development on the modeling side. There have been many attempts on improving the models or approach to solve a turbulent flow itself. So, overall the turbulence modeling is classified as Rand's approach, where we solve time averaged Navier-Stokes equation. All turbulent length scales are modeled in the Rands, and we have, depending on how these quantities or variables are related, how these quantities mean, you have turbulent kinetic energy, specific dissipation rate, length scale, the equation for length scale. Depending on how these are related, we get different turbulence model, and this is one of the successful or most widely used approach for calculating industrial turbulent flows. You also have under this different classification, what is known as the algebraic model or zero equation model, one equation model, two equation model and second order closure model. So, this zero equation, one equation and two equation represent number of additional PDE you will use to solve or to represent a turbulent flow. The second approach is what is known as a direct numerical simulation. As the name indicate, you obtain solution without following any modeling strategy. So, theoretically all turbulent, that is laminar and transition flows, can be simulated by numerically solving the full Navier-Stokes equation. As I mentioned before, the structure of the turbulent flow equation is the same as the original Navier-Stokes equation. If you interpret the variable as instantaneous, then it is for turbulent flow, otherwise it is for laminar flow. So, it is possible to use the same equation even for turbulent flow, and if you solve or if you resolve all the scales, it is all the scales corresponding to velocity, length and time, then you get what is known as a direct numerical simulation approach. So, it resolves whole spectrum of scales, absolutely no modeling is required. On the other hand, though it looks very good, there is a great disadvantage. The cost is exorbitantly prohibitive. It is very high, because in order to resolve all the scales, you need to have mesh resolution as well as delta t very fine enough. That is very expensive, and it is tried only as academic level, not attempted for any industrial flows problem. The other approach is what is known as a large eddy simulation. In short form, it is called LES. It solves spatially average Navier-Stokes equation, where large eddies are directly resolved, but smaller eddies smaller than the mesh that is used are modeled. It is less expensive compared to DNS, but slightly more compared to RANS. The amount of computational resources and efforts are still too large. In recent, there have been attempts to use LES for industrial problems as well. There is alternative approach, what is known as a hybrid approach, whether you can combine RANS and LES appropriately. So, depending on how they are combined, you get a solution, and this is called hybrid approach. Some literature they call with a special name what is known as detached eddy simulation, otherwise DES. We have three approaches: RANS, LES and DNS, and in between there is a strategy hybrid approach. Now, we go into the equation once again. I am displaying here the RANS equation, time average Navier-Stokes equation, and we know this stress term, and we identify normal stress as well as shear stress. We also identify off diagonal elements shear stress are symmetric with respect to the diagonal. Hence, total number of unknowns coming through Reynolds stress is only 6, 3 diagonal normal stress term and 3 off diagonal shear stress term. In the conventional form, it is written with the time with material derivative or total derivative on the left hand side. On the right hand side, we have pressure derivative term. The second term based on laminar viscosity is written as a laminar stress, and third term based on turbulent stress is written as here turbulent stress. Now, the question is whether it is possible to get equation for stresses, because we mentioned in the closure problem that we have 10 unknowns now, but you have only 4 equations. There are 2 approaches: either you get additional transport equation for those additional stresses or new unknowns, or replace the unknowns by a known. In the first approach, that is trying to derive equation for additional unknowns, we will end up getting more unknowns. We are going to derive equation for those unknowns, and at the end you will observe that you get only more unknowns rather than closing the problem. So, this is the equation that is obtained for fluctuation. In this equation, we use I and K, and these are obtained very systematically following all the arithmetics. That is, you have an instantaneous decomposed into summation of mean and fluctuation. You apply this decomposition, then you get equation for fluctuations. Now, this is just a representation, in the sense the index notation I is very generic. So, you can replace that index I by j and get equation for another fluctuation. In other words, you have one equation for one fluctuation, you have another equation for the second fluctuation. So, if you multiply the above equation by uj prime and the second equation with the ui prime, then take average. So, for each term that operation is performed, each term you multiply by uj prime in this, then similarly in this each term is multiplied by ui prime, then you do average, then you get finally an expression as shown here. It is purely arithmetic and it is possible to obtain the final expression as shown here. Now, if you look at this expression, the term variable term is actually ui prime uj prime bar, that is a variable in this equation. Hence, our desire, the starting desire is to get additional PDE for this unknown is obtained. However, when you look at this equation in closed, you will observe that you are getting a new term, the third order correlation term ui prime, uj prime and uk prime bar. So, this ui prime, uj prime, uk prime bar is a new unknown, and you can identify that by substituting value for I, j and k, you get so many unknowns. Actually, you get 27 new unknowns. Now, we understand the closure problem can never be achieved. So, there is alternative way that we have to plan, and that is what we are going to see in turbulence modeling. So, in this equation again we follow one step in the tensor algebra, what is known as a contraction. The contraction is nothing but taking a trace or taking the isotropic part. So, if you substitute I is equal to j, then you get all diagonal elements in the Reynolds stress tensor. So, we get one equation for each normal stress term. For example, if you substitute I is equal to 1 and j is equal to 1, it becomes first normal stress, I is equal to 2, j is equal to 2, you get second normal stress, I is equal to 3, j is equal to 3, you get third normal stress, and you follow that for all the terms. Then you get equation for each normal stress. And in trace procedure contraction, because its index is repeating, you do summation, and that is written here k, which is a symbol used for denoting turbulent kinetic energy, is tau II by 2, and tau II is nothing but normal stress. Because we are doing trace, it is summation u1 squared u1 prime squared bar plus u2 prime squared bar plus u3 prime squared bar, and we follow this. Then on this equation, that is a transport equation for Reynolds stress, if you apply the trace procedure for each term, and then after following some step, you get finally an equation for turbulent kinetic energy. So, in this equation k is a variable and you get equation for turbulent kinetic energy. Now, in this equation again we have multiple terms. First term is unsteady term, second term is a convection term, third term, which is the first term on the right hand side, is a production term, fourth term is a dissipation term, and there are three subterms in for fifth term. The first term for the fifth term is a molecular diffusion term, second term for the fifth term is a turbulent diffusion term, and third term, the first term is a pressure diffusion term. Let me give some more explanation. The second term on the left hand side is a convection term. This has uj as a convection velocity and dou k by dou xj is a variable and its corresponding spatial derivative. Now, when you look at this term and again try to compare the convection term in the momentum equation, convection term in the momentum equation is non-linear, whereas this is linear. Now, first term on the right hand side, which is marked here as a third term, this is what is called production term. Tau ij is a Reynolds stress term and dou ui by dou xj is for the mean velocity gradient, and this is a product of Reynolds stress with the mean velocity gradient that will give you what is known as a production of turbulent kinetic energy. Then fifth term, there are three terms. First term is because of the molecular viscosity, hence it is called molecular diffusion term. The second term, we have turbulent quantities, turbulent fluctuating quantity, and we can interpret this uj prime, one quantity uj prime is a agent responsible for transporting this turbulent stress. We know ui prime, uj prime is a turbulent stress, and you have additional term uj prime. So, we can interpret this term as a turbulent diffusion term, and third term is a pressure diffusion term. Now, the question is, all are supposed to be known except for second term as well as third term and dissipation term. So, in today's class we have learned the first stage in the turbulence modeling, starting from transport equation for each Reynolds stress term and how to get the trace of it to obtain what is known as a transport equation for turbulent kinetic energy. In the next class, we will start from here and do actual modeling for those additional terms in the transport equation for turbulent kinetic energy, and we go into standard k epsilon and k omega model expression and explanation. Thank you.